This is the first video on our nuclear energy series of revision for AQA. We're going to look at the classic physics equation E equals mc squared, look at what it means, do some silly calculations and then some more useful calculations, and apply all this to at the end of the lesson sort of alpha and beta decay. So first up, let's just remind ourselves, in 1905 Einstein published his special theory of relativity. It is one of the option modules in AQA. You don't have to look at it for the normal exam if you're not doing that option. Some things he found: moving clocks run slower, moving objects appear shorter, moving objects mass changes with speed, and the speed of light c is the maximum possible speed, and it's the same for any observer. And one of the equations that came out of his work was E equals mc squared. So we're saying here that the mass of an object increases or decreases when it gains or loses energy. On one side of this equation you've got energy, on one side you've got mass, and c squared is a constant. So this is purely an exchange rate idea, that energy is the same as mass, and it's exchanged with the exchange rate being linked to the speed of light squared. So what we could do is do some maybe silly calculations. So we can estimate the increase in mass of a car that speeds up from standstill to 30 meters per second. A car increases its energy when it goes from 0 to 30 meters per second. If it increases its energy, it therefore must increase its mass. How much? Well, let's have a look. Half mass v squared, I've assumed 1,000 kilogram car, 450,000 joules. Then we'll shove it in m equals E over c squared, just rearranged Einstein's equation, and we've got an increase in mass of 5 times 10 to the minus 12 kilograms, so not a lot. Let's do the same for water. Let's increase 1 kilogram of water by 10 degrees. If you remember your work on specific heat capacity, this is 42,000 joules of energy it will take to do this. So again, m equals E over c squared, 42,000 over 3 times 10 to the 8 all squared will give an increase in mass of the water of 4.7 times 10 to the minus 13 kilograms. So are they significant? No. And what percentage change in mass occurs? You can work it out if you want, but it is an unbelievably small. It's going to be 5 times 10 to the minus 12 divided by 450,000. So it's going to be 1, 2, 3, 4, 5. It's going to be something like 10 to the minus 17%. So totally insignificant. Okay, but is it more significant for a nucleus? So let's do a calculation. Calculate the change in mass of a polonium nucleus, mass of 3.49 times 10 to the minus 25 kilograms, that releases a 5 mega electron volt alpha particle. So if this releases 5 megavolt alpha particle, let's have a look what happens to the mass. M equals E over c squared, so 5 times 10 to the 6. There's the mega electron volts, so let's convert this to joules. Remember this equation, E equals mc squared, you always need to be in joules. So times 1.6 times 10 to the minus 19 divided by the speed of light squared gives you an answer of about 9 times 10 to the minus 30 kilograms. Which is approximately 10 to the minus 29 kilograms. Is this significant? Well, if you do the percentage change, it's about 0.003%. So, okay, you might say not very significant, but at least it's something we can ponder, think about. It's not something crazy like 10 to the minus 17% as it was. All right, so what are we showing here? Well, we can tell the energy stored in something by measuring its mass. Normally, this effect is too small to measure, since the increase in mass is caused by increasing the energy by even millions of joules is very small. Because of the exchange rate of being 3 times 10 to the 8 squared, you need a lot of energy to create a tiny amount of mass, or be converted to a tiny amount of mass. Okay, but reactions on a nuclear level do involve significant changes in mass, so we can calculate the energy released using Einstein's equations. Let's just do a couple of examples. Alpha decay and mass change. Thorium decays by an alpha emission into radium-224. Write a decay equation and use the following data to calculate the difference in mass and so the energy released. Here's all the information you'd need. Okay, so you've got mass of thorium, radium and alpha in U, and using the conversion on the data sheet, that 1 U which is an amount of mass, is equal to 931.3 mega electron volts. So we can use that right at the end. So first of all, let's write the decay equation. Here it is. Thorium decays to radium with the alpha particle. Now let's put our idea that the mass difference is the initial mass minus the final mass. So the initial mass is 227.97929, which is this thorium, minus the two things that come out, which is radium and alpha. And if you do all this, you get a mass difference of 0.00590 U. Then we can use our conversion, so 0.00590 U times 931.3, our conversion up here, which gives us 5.49 mega electron volts. Okay, so that's the difference in mass first and the energy released in electron volts, or mega electron volts as we've done it there. Okay, so let's now beta decay and mass change. So aluminium 29 decays by beta to silicon 29. Write a decay equation and use the following data to calculate the difference in mass. Just like before, everything you need is there. So here's our decay equation. Aluminium decayed to silicon with the beta negative and the antineutrinos coming out. Again, mass difference is initial mass minus final mass. So the initial mass is the aluminium, 28.97330, minus the silicon and the beta particle, the electron, and I've put in a 0. The mass of the neutrino is negligible, so we don't have to worry about that. If we put all that in our calculator, you should get a mass difference of 0.00395 U, and then we can use our conversion, multiply it by 931.3 to give us an answer of 3.68 mega electron volts. So just note at the bottom, use U when given, and then energy in electron volts, and the mass of the neutrino is negligible. So last little bit, where does the energy go? This energy is obviously has got to come out. We've got to account for it. So we've account for it in terms of numerically. But what actually happens? Well, in alpha decay, the nucleus recoils when the alpha particles are emitted. So the alpha particles always released with the same energy. If you think the same masses are involved, so we've got a conservation of momentum idea. So every time a particular isotope decays via alpha, the momentum of the two particles is the same, or the total is the same, and this energy is the energy released is shared between the alpha particle and the daughter nuclei, and the alpha particle gets most of it. So we can do a quick calculation for that with thorium 228 decaying by alpha into radium. Let's have a look. We've got the kinetic energy is half mv squared. Let's rearrange that. V equals root 2 EK over m. So here we've got momentum is mass times volume. Momentum is mass times velocity, sorry. Rearrange that. Momentum is mass times velocity, our expression for velocity here. M root 2 EK over m. Just going to mess around with this a little bit. If I pull this m out and have m over root m, so I've got momentum is m over root m, multiplied by the root of 2ek, and all of that basically is equal to root 2 MEK, because m over root m is the same as root m. So I can just cancel this out and just put a root m back in that expression. Okay, so let's just use our momentum idea. Momentum before equals momentum afterwards. 0 would be the momentum of the alpha particle plus the momentum of the nucleus. So in terms of magnitude, these must have the same magnitude. The momentum must have the same magnitude, so we can write a little expression here using our derived expression here for momentum. 2 times the mass of the alpha, the kinetic energy of the alpha, rooted must be equal to 2 times the mass of the nucleus, kinetic energy of the nucleus, rooted. And here I'm using this idea that the two momentums must be equal. So now we can square both sides. We end up with that expression. Just jiggle it around a bit, so we've got the ratio of the energies, the ratio of the masses, and this, hopefully, if we just put some numbers in now for the mass of the nucleus divided by the mass of the alpha. In our case, it's 224 over 4. Radium's got 224 nucleons, and alpha particles just got 4. So you can see here that the alpha particle gets a ratio of 224 to 4 of energy, or i.e. 224 over 228 in terms of a fraction, i.e. pretty much all of it. All right, and in terms of beta decay, it's more complicated because we've got the energy being shared between the nucleus, a beta particle, and a neutrino or antineutrino, if it's depending whether it's a positron decay or beta negative electron decay. So because this energy can be shared in any ratio, the beta particles can have a continuous spectrum of energies. It's not as simple as the alpha decay, whereas the alpha particles always come out with a particular energy.